Welcome students. In this third semester in organic chemistry paper, we deal with ultraviolet visible spectroscopy technique. To start with, let me give a general introduction to spectroscopy. First of all, what is spectroscopy? Spectroscopy, as we know, is the study of interaction of electromagnetic radiation with matter, and when after interaction of the electromagnetic radiation with the matter, if we measure the absorbed or transmitted energies and plot them against the wavelength of absorption or transmission, we get a spectrum. Now, the electromagnetic radiation has a range, a vast range, starting from the longer waves of radio waves to short wave gamma rays, and each and every of these radiations interact with matter in many different ways to give rise to different techniques. The radio waves, for example, interact with the spin orientations of certain magnetic nuclei, and the technique that arises from the interaction of the radio waves with the matter is said to be NMR, nuclear magnetic resonance spectroscopy. And the microwaves interact with the matter to give rise to two techniques: electron spin resonance spectroscopy technique and rotational spectroscopy technique. The ultraviolet and visible radiations excite the electrons present in a substance, and the resulting technique is electronic spectroscopy. And the IR radiation can cause changes in the vibrational motions of the molecules, which gives rise to vibrational spectroscopy. The X-rays are responsible for X-ray diffraction and X-ray photoelectron spectroscopy, and the gamma rays cause changes in the nuclear energy levels to produce mass by air spectroscopy. So, this is a general introduction to spectroscopy. Now, let us come to our topic: ultraviolet and visible spectroscopy. The ultraviolet and visible spectrum, that is visible radiation, ranges from 200 nanometer to 800 nanometer, of which the ultraviolet radiation alone ranges from 100 nanometer to 400 nanometer. From 400 to 800 nanometer, the visible radiation ranges. Now, when we take ultraviolet visible spectroscopy of a substance, we scan this range from 200 nanometer to 800 nanometer. Now, in the principle of ultraviolet visible spectroscopy, the substance is excited using ultraviolet visible spectroscopy. That is, the electrons of the substance are excited from their bonding molecular orbital to the antibonding molecular orbital. And after the interaction of these radiation, ultraviolet visible radiation, when the expended energies are plotted against their corresponding wavelengths, the resulting spectrum is a ultraviolet visible spectrum. In the far corner of the spectrum, in the far corner of the board, I have given a drawing of the spectrum, a typical ultraviolet visible spectrum, which is actually an inverted parabola. And this spectrum provides two quantities for analysis. First is lambda max, the maximum of the peak. Second is the intensity. From these quantities, we can infer information about the substance. So, for example, for isoprene, the lambda max is given by 222.5 nanometer, and the molar absorptivity is given by 10,800. The molar absorptivity also, it has units, it is represented without any units, but the wavelength of maximum absorption is represented by the nanometer. Now, the ultraviolet absorption by a substance is governed by Beer-Lambert's law, which is given by log I0 by I is equal to ECL, where I0 is the intensity of the incident radiation, I is the intensity of the transmitted radiation, E is molar absorptivity or molar extinction coefficient, C is concentration of the sample, L is the path length, and this log I0 by I can be given by A, absorbance, and this absorbance is evidently proportional to concentration and path length, which one equaled A is equal to ECL. I said the electrons of a substance are excited during ultraviolet visible spectroscopy technique, and there are different different types of electrons present in a molecule. For example, the electrons can be classified into three types: sigma electrons, pi electrons, and n electrons. Sigma electrons are present in a sigma bond. A sigma bond is formed by the head-to-head overlap of orbitals, and this is the strongest bond. Then comes pi, because a pi bond is formed by the sideways overlap of the orbitals. Now, in the case of sigma bond, the sigma bonded electrons are excited to the sigma bonding antibonding orbital, and in the case of pi electrons, the electrons are excited from pi bonding orbital to pi star antibonding orbital. The n electrons are also excited, and the n electrons are excited either to the pi star antibonding orbital or sigma star antibonding orbital. Now, let us take all these different types of electronic transitions one by one. So, in all there are 4 different types of electronic transitions: sigma to sigma star, n to sigma star, pi to pi star, and n to pi star. First, let me take the sigma to sigma star transition. Now, the sigma to sigma star transition is a high energy transition, which means the energy that is required for the excitation of electrons does not fall under the normal range of 200 to 800 nanometer. It goes vacuum, that is, we need to produce vacuum ultraviolet conditions, that is around 120 nanometer. For example, alkanes shows the sigma to sigma star transition because alkanes contain only the sigma electrons. The next transition is n to sigma star transition. Some compounds have the n electrons. For example, those compounds having electronegative elements like oxygen, nitrogen, halogens, etc., RX, ROH, RNH2, etc. And these n electrons can be excited to the sigma star antibonding level, and the energy is a broad range, that is 150 to 250 nanometer, depending upon the substituent that is present in the alkyl moiety. And then next, pi to pi star orbital, pi to pi star transition, pi to pi star. In the case of pi to pi star, the range is from 170 to 190 nanometer absorption range, and the compounds that show the pi to pi star transition are alkenes, aldehydes, and ketones. The pi to pi star transition is called as a K band. K in German means conjugate, because the pi to pi star transition is mainly dealt with for conjugated compounds and aromatic compounds, and that is the reason why it is said to be a conjugate band. And then finally, n to pi star transition. The n to pi star transition usually ranges from 270 to 300 nanometer, and it is shown by compounds possessing n electrons and pi electrons. For example, aldehydes and ketones. The band is said to be R band or representing radical. It is said to be a radical band because it is a forbidden transition. According to the symmetry rules, the n to pi star transition is forbidden. So, the molar absorptivity value for a n to pi star transition will be around 30 to 40. Now, certain terms in ultraviolet visible spectroscopy technique can be defined. First, chromophores. Chromo means color and force means bearer. So, chromophores are color bearers, which means those covalently unsaturated groups that are responsible for color are called as chromophores. For example, C double bond C, C double bond O, NO2 are some of the examples. Second, oxochromes. Oxochromes are those groups which enhance the color of the chromophores. That is, oxochromes themselves are not responsible for color, but they assist chromophores in enhancing the color. Oxo means increase and chromo means color. So, the increase color increases. For example, those compounds with the non-bonding electrons, for those functional groups with non-bonding electrons, for example, OH, NH2, Cl. The next topic, the next term can be bathochromic shift. Bathochromic means that is when the shift of absorption maximum is toward longer wavelength, it is said to be a bathochromic shift. The next hypsochromic shift, when the shift of absorption maximum is toward shorter wavelength region, it is said to be a hypsochromic shift. And then hyperchromic effect, when absorption intensity is increased, then it is said to be hyperchromic effect. Increased absorbance or increased absorptivity. In hypochromic effect, the absorption intensity is decreased, that is, there is a decrease in the absorbance or absorptivity. Next, we shall see the factors affecting the position and intensity of absorption. Now, I have shown on the board the ultraviolet visible spectrum of a compound, and there are two quantities in this spectrum, the lambda max or wavelength of absorption, and second intensity. This lambda max is a characteristic of a substance, and from the lambda max we can find out information about the substance. The epsilon value also yields information about the substance. The epsilon value usually yields information about the intensity of the absorption. The intensity is above 10,000 in the case of an allowed transition, or it is less than 1000 in the case of a forbidden transition. So, there are strong absorptions and weak absorptions, and it is shown by the intensity. Now, let us come to the position of the absorption bands. The position of the absorption bands are influenced by the solvent in which the sample has been dissolved, and they are also influenced by the structure of the sample. So, the first factor that affects the position of absorption is solvent, and the second factor that affects the position of absorption is the structure of the sample. Now, I said there are 4 different transitions: sigma to sigma star, n to sigma star, pi to pi star, and n to pi star. Of these 4 different transitions, 2 are very useful, that is n to pi star and pi to pi star. They are R band and K band respectively. These bands are the most useful bands, most useful transitions, because they are accessible by the instrument, that is in the range that we scan from 200 nanometer to 800 nanometer. Now, these 2 transitions are adversely affected by the nature of the solvent. Now, in case we take a sample which is dissolved in a polar solvent, and we shall also assume that that solvent has a carbonyl group. Now, when a compound contains carbonyl group, there are 2 different kinds of electrons there, that is the n electrons and the pi electrons. So, we can actually draw a schematic in order to represent the energy aspects of the sample. Now, in this particular diagram, I have shown a pi to pi star transition, and in between pi to pi star levels, there are n levels, and from the n level the electrons undergo transition to the pi star level, and when the sample is solvated, that is when it is dissolved in a polar solvent such as an alcohol, the situation of the energy schematics is as shown. You can see in the diagram there is a pi to pi star transition in the original position, but the n level is a bit low or down, and this makes the gap between n and the pi star high. In the first schematic, the gap between the n and pi star is low, but in the second, the n and pi star gap is high, which means a large amount of energy is necessary in order to promote the n electrons to the pi star level compared to the original situation. How this happens? This happens because the carbonyl groups are solvated by the alcohol, that is the lone pair electrons present on oxygen are engaged by the hydrogen. So, as a result, because of this strong bound nature of the lone pair electrons, the electrons cannot that easily be excited to higher pi star level. They are now tightly bound, strongly bound. So, as a result, the n electrons cannot be excited easily, and not only that, the energy level also becomes low because the electrons are solvated. Their overall energy level comes down. So, as a result, the R band or n pi star transition undergoes blue shift in polar solvent, that is the wavelength of maximum absorption moves toward shorter wavelength region. Okay, then second, K band, pi to pi star. How K band is affected because of the presence of polar solvent. In this case, that is in the case of K band, a pi to pi star transition, the sample shows a red shift, that is the transition shows a red shift in polar solvent, that is the lambda max moves towards longer wavelength region. Now, the two schematics, normal and the solvated schematics, are shown in the figures. In the normal schematic, there is a pi to pi star level and it is high in nature, but in the case of solvation, something happens, that is the level of the pi star comes down. This is because the pi star is more polar in nature, and so a polar pi orbitals, anti-bonding orbitals, are solvated by the polar solvent, and as a result the energy level of the pi star becomes low. As it becomes low, the energy gap between the pi and the pi star in the second schematic becomes low. So, now less energy is enough to excite the electrons from the pi bonding orbital to pi star anti-bonding orbital. That is the reason why a K bond or pi to pi star transition shows a red shift in polar solvent. So, this is about the position of the lambda max affected by solvent. Second factor which affects the position of absorption band is the structure of the sample, that is the molecular structure of the sample. Two factors can be considered here. The first factor is ring strain, the second factor is ionization. Let us take the first factor, ring strain. Let me take as an example verbenone, a compound which has a ring, and in this compound the wavelength of absorption calculated is around 239 nanometer, but when the compound is recorded, the UV visible spectrum shows an absorption maximum of 253 nanometer. Now, there is a gap of 14 nanometer, that is there is an increment of 14 nanometer, which seems to be due to the ring strain that is in this verbenone compound. Second, ionization. For ionization, let me take as an example acetyl acetone. The structure of the acetyl acetone is shown here, and when it analyzes, this is the structure that is shown for acetyl acetone, and when its wavelength of absorption is calculated, it comes to around 257 nanometer. But when its UV visible spectrum is recorded, it shows a wavelength of absorption at 293 nanometer, and this is due to ionization. The ionization results consequently in the sharing of hydrogen bond between the carbonyl carbon and the oxygen, and it produces a structure which is conducive for extensive delocalization, and as a result the absorption maximum shifts towards longer wavelength region. We have seen the position of absorption. Now let us see the intensity of absorption. The intensity of absorption is governed by factors such as concentration, path length, transition probability, and structure. Now first, concentration. The more the concentration, the greater will be the absorption of radiation and higher will be the intensity. So if the sample is highly concentrated, the light will be absorbed more. Second, path length. Path length refers to the size of the sample, which may vary from 1 to 10 centimeter, but usually in our spectrometers we use 1 centimeter sample cell. The third factor is transition probability. Transition probability refers to the allowedness and forbiddenness of a transition. For example, an allowed transition will be more intense compared to the forbidden transition. The allowedness and forbiddenness of a transition is indicated by the molar absorptivity value or molar extinction coefficient value, which for an allowed transition will be around 10,000, and for a forbidden transition it will be less than 1000 or around 1000. Then the fourth factor is structure. The sample molecular structure also affects the intensity. For example, we can take this compound. This compound has a steric hindrance, and because of its steric hindrance, although the lambda max value is observed at the calculated range, the Emax, that is molar absorption coefficient or molar absorptivity, is less, that is around 1400. So this less intensity is caused by steric hindrance present in this molecule. Now let us see the absorptions of dienes, polyenes and unsaturated carbonyl compounds. Let me take first dienes. Before going to the dienes, let me deal with the simplest alkene, ethylene. If you take the ultraviolet visible spectrum of ethylene, it shows a maximum around 162 nanometer for the pi to pi star transition. All alkenes absorb around 160 nanometer. Now if one more ethylene is added to that ethylene, it forms a compound called butadiene, 1,3-butadiene, and 1,3-butadiene is seen to absorb at 270 nanometer, that is its pi to pi star transition shows absorption at 270 nanometer lambda max. And if one more ethylene group is added, it forms a compound called 1,3,5-hexatriene, which absorbs around 256 nanometer. So there is a steady increase of wavelength from 162 nanometer to 256 nanometer. From 162 to 217 it is 55 nanometer increase. From 217 to 256 it is again around 36 nanometer increment. Now what is the reason for this? Let us consider the schematics of ethylene, butadiene and polyene, that is the pi energy schemes. For ethylene, it is as shown in the figure on the board. The schematics is shown. There is a pi bonding orbital and there is a pi star anti-bonding orbital, and the pi bonding electrons, one of the pi bonding electrons is excited to the pi star anti-bonding orbital. But when 2 more pi electrons are added, 2 more pi orbitals are added, now there are 4 pi electrons, which means there are 4 pi orbitals. Now these 4 pi orbitals combine among themselves to produce 4 equivalent new molecular pi orbitals, and these are shown in the figure, that is pi 1, pi 2, pi 3 star, pi 4 star, 2 bonding, 2 anti-bonding. And if you see, the pi 2 and the pi 3 star are close lying energy levels. So it is very easy to excite an electron from pi 2 to pi 3 star, because pi 2 is a HOMO here, that is HOMO means highest occupied molecular orbital, and pi 3 star is LUMO here, that is lowest unoccupied molecular orbital. So as electrons were excited from pi to pi star in the case of ethylene, in the case of butadiene, the electrons are excited from pi 2 to pi 3 star. Now if more number of pi electrons are added, what will happen? As in the case of a polyene, as the number of pi electrons are added, number of pi orbitals are added, and these pi orbitals combine to produce equivalent new pi molecular orbitals, bonding orbitals and anti-bonding orbitals, and transitions from the highest occupied bonding orbital to lowest unoccupied anti-bonding orbital will always take place, and as a result there is a shift of absorption wavelength from the shorter wavelength region to the longer wavelength region. So this is a reason why, because of the addition of new orbitals, the wavelengths shift from the shorter wavelength region to the longer wavelength region. Okay. Next, structural features affecting absorptions. Not only the addition of pi bonds, but the structural features also affect the absorption bands, that is absorption of bands. First structural feature is geometrical isomerism. Let us take 2 cases or compare the 2 cases, trans-stilbene and cis-stilbene. In the case of trans-stilbene, the absorption takes place at 295 nanometer, but in the case of cis-stilbene, the absorption takes place around 280 nanometer. That is, trans-stilbene absorbs 50 nanometer higher compared to the cis-stilbene. What is the reason? In the case of trans-stilbene, the molecule maintains its coplanarity, that is, there is extensive delocalization, there is no disruption in delocalization of pi electrons. So as a result, the pi electron delocalization is facilitated, and this makes the compound to absorb at a longer wavelength. But when we come to the cis-stilbene, there is no coplanarity, that is, coplanarity is disrupted. So the compound absorbs at a lesser wavelength, 280 nanometer, shorter wavelength, that is, there is no extensive delocalization which to facilitate absorption at a longer wavelength. That is the reason why more energy has to be expended for this compound in order to show lambda max, that is pi to pi star transition, and it is 280 nanometer. Now in the second factor is cis-side and trans-side conformations. Now there are two different types of conformations, cis-oid and trans-oid, S-trans and S-cis, or S-cis or S-trans. The S denotes single bond, that is about the single bond. The double bonds can be disposed in two ways, either in a conformation anti to each other or in a conformation syn to each other, that is cis. So in the case of S-trans, the double bonds are disposed, that is in a trans manner, and this butadiene, trans butadiene, for example, absorbs at 270 nanometer. But in the case of cyclohexadiene, the cyclohexadiene has cis conformation which absorbs at 256 nanometer. So the S-cis conformation always absorbs at a longer wavelength compared to the S-trans conformation. Again, this is because of the maintenance of delocalization, good delocalization of the pi electrons in the case of cyclohexadiene compared to the S-trans situation. Now let us take the case of polyenes. Polyenes are compounds with many double bonds. In the case of polyenes, there are a number of pi electrons and so a number of pi orbitals, and these pi orbitals combine among themselves to produce new molecular orbitals, equal number of new molecular orbitals, and because of the close lying nature of the energies of these orbitals, there is easy transition from the bonding pi molecular orbital to the anti-bonding pi star molecular orbital. For example, let us take the case of lycopene. This is a compound with 11 double bonds, which means there are 22 pi electrons. So 22 pi electrons combine among themselves to produce 22 new equivalent molecular orbitals, and there is transition between these energies of molecular orbitals, and this compound appears red in color. For example, the red color of the tomatoes is due to this compound. This compound is abundantly present in the tomatoes, and if you see, this compound absorbs in the visible radiation, that is, its compounds appears red, so it absorbs evidently in the visible region of the electromagnetic radiation, and these are the peaks, that is absorption bands, absorption lambda maxes for the lycopene, 453 nanometer, 471 nanometer and 502 nanometer respectively, and this is due to the many close lying energy levels of the pi molecular orbitals in this polyene. Now we shall take the case of unsaturated carbonyls. Let us take the case of a normal carbonyl first. A normal carbonyl bond shows the following absorptions, that is pi to pi star around 150 nanometer, N to sigma star around 190 nanometer, and N to pi star around 280 nanometer. But if a pi bond is added to the normal carbonyl, what will happen? In order to illustrate this point, let us take two cases, ethyl methyl ketone and methyl vinyl ketone. In the case of ethyl methyl ketone, the pi to pi star band shows a maximum at 185 nanometer, but in the case of methyl vinyl ketone, the same band appears at 290 nanometer. In the case of ethyl methyl ketone, for example, N to pi star band shows a maximum at 277 nanometer, but in the case of methyl vinyl ketone, the same band appears at 324 nanometer. Now why this difference? This difference is due to the addition of pi electrons, a pi bond to the normal carbonyl. Addition of pi electrons produces conjugation, more pi delocalization, production of newer pi molecular orbitals, and so now energy can very easily excited from the lower energy levels to the higher energy levels because of the many number of close lying energy levels.